Hello friends, so in the fourth video of elimination reaction, we will talk about the regiochemistry in E1 and E2 mechanism, that is basically the Saytzeff versus Hofmann product. So first of all, we have to know the position of the double bond. That is actually whether it is Saytzeff product or Hofmann product. So elimination reaction, it may be regiospecific or regioselective. So what is regioisomer? That is the same functional group if its position is different in a molecule. For example, if you look at these molecules, this carbonyl group, there is a methyl group also, fine. But the methyl group is changing its position. Here it is at 2 position with respect to carbonyl. Here it is at 3 position. Here it is at 4 position. So all these 3 molecules, they are regioisomer to each other. In a similar way, if you look at these 2 molecules, in the first case, the double bond is terminal. In the second case, the double bond is in the middle. So it is more substituted double bond compared to the first one. Now, what is regiospecificity and regioselectivity? Suppose in a reaction, there is a possibility of formation of 2 or more than 2 regioisomers, but only exclusively one of the product you are getting. So that in that case, we will call the reaction regiospecific. But suppose there are possibility of 3 products, but you are getting one of them as major. So in that case, we will call the reaction as regioselective. So that is the difference between regiospecific elimination and regioselective elimination. Fine. Next, we will see what is Saytzeff rule. So if in the elimination, we know there is a formation of alkene. So if our alkene is more substituted alkene, then we will say that Saytzeff rule is followed. But if less substituted alkene is produced, we will say that Hofmann rule is followed. Now, more substituted alkenes are more stable. So why it is so? Here there are some examples. Tetra-substituted alkene. You can see here we have 4 methyl groups. Tri-substituted 3 methyl groups. All the methyl groups are highlighted here. 2 methyl groups, and in the last one there is only 1 methyl group. So more substituted alkenes are more stable than less substituted one. And the reason is because of hyperconjugation. Now what is hyperconjugation? Suppose this is a pi bond, okay, parallel overlap between 2 p orbital, and if there is a methyl group just beside this double bond, then there is some interaction between this pi bond and this CH sigma bond. So more is the number of this type of methyl group, not just methyl group or any other alkyl group. So more will be the hyperconjugation. So higher is the amount of this interaction, that is the hyperconjugation. Higher is the stability of that alkene. So that is the reason that more substituted alkenes are more stable. Okay, so you can say that Saytzeff alkene, that is a more substituted alkene, that is more stable than Hofmann alkene. Fine. So here we have a molecule which is 2-bromopentane. Here you can see I have highlighted 2 different types of beta hydrogen. So this is beta hydrogen, all these 3 hydrogens, they are beta hydrogens. And on the left hand side, these 2 hydrogen, that is also beta hydrogen. Because if you consider this carbon as alpha, because our leaving group is attached to this carbon. So with respect to this carbon, these green hydrogens are of beta hydrogen, these blue hydrogens, that is also beta hydrogen. Now when we are using base, and if this beta hydrogen, it is removed together with this leaving group, you are getting more substituted double bond. But in the opposite case, that is in the right hand side, these blue hydrogens are removed, you are getting less substituted alkene. So this is a terminal alkene. So what is the difference? Obviously the first product is Saytzeff product, and the second product is, that is on the right hand side, the product that you are seeing, that is Hofmann product. So what are the difference between these two? Saytzeff product, it is more substituted. Hofmann product, it is less substituted. It is produced by the removal of hydrogen from the beta carbon, which is bonded to the fewest hydrogen atoms. So if you look at the left hand side, there are only 2 beta hydrogen. But Hofmann product is produced by the removal of hydrogen from the beta carbon bonded to highest number of hydrogen atom. If you look at this side, there are total 3 beta hydrogen. But this side, there are 2 beta hydrogen. Okay. Now Saytzeff, that is generally, though it is not the specific always, it is not exclusive, generally most of the cases the most stable alkene is the most substituted alkene. In most of the cases, remember, not always. We will also see some cases where you will see that this rule is not followed. Okay, so generally the most stable alkene is the most substituted alkene, and least alkyl substituted are attached on the double bond in this case. So the double bond that is produced here, you can see on the right hand side there are 2 hydrogens attached with this carbon, and on the left hand side carbon there is this propyl group attached. But if you look at the more substituted carbon, on the right hand side carbon 1 hydrogen and 1 methyl group, and on the left hand side there is 1 ethyl group and 1 hydrogen attached. Okay. Next we will see the regiochemistry in E1. So in E1 elimination, it is regioselective. According to the definition of regioselectivity, there are possibility of product formation of 2, but among them only 1 will be major. Okay, so it generates that alkene that has the more substituent as the major product, which is clear from the products that you are seeing here. Fine. Now this is because here the leaving group departs to produce first a carbocation. We know that this is our intermediate, right? Now after that, in the second transition state, this is the first transition state where the carbocation is produced. So this is our intermediate. Now in the second transition state, you can see on the left hand side there is 1 hydrogen, 1 beta hydrogen with respect to this carbocation that can be removed, and on the left hand side also there is another beta hydrogen that can be removed. So more substituted alkene it is produced as a final product. Yes, that is fine. That is more stable, so that is why it is producing. That is not the only reason. We also have to see the transition state. So here both the transition state that are leading to these 2 different types of product that is shown here. So you can see some double bond character is generating because of some hyperconjugation, and hyperconjugation that is also taking place here, that is with this hydrogen. But what is the difference between these two? As we are talking about hyperconjugation, so double bond character that will already be felt in the transition state. So obviously if there are more substituents, that alkene, the stability of that alkene, it will be already felt in the transition state. Fine. So that is the reason that this product will be major. So it means that in E1, Saytzeff rule is followed. Okay. Now what about regiochemistry in E2? Now most of the E2 reactions where your leaving group is very good, that is halide, sulfonate, etc. types of leaving groups, then Saytzeff rule will be followed. And the reason is just same as before, when the leaving groups are very good. So this can be attributed to similar transition state, similar same type of logic we can apply. So here we will see with an example. So our molecule is CH3, CH2, CHBr, CH3. Fine. If you look at this box, there are beta hydrogen on the left hand side, also beta hydrogen, that is beta B, blue colored hydrogen, that is on the right hand side. So if beta B hydrogens are removed, this is your alkene, and if green colored beta hydrogen that are removed, then this is your more substituted alkene. Now if you look at the transition state, that is, you know, in E2 there is a single transition state, it is concerted process. The double bond character, it is already felt in the transition state. So the transition state which is leading to the Hofmann product, that has higher energy. So this is the energy gap between these two. And the transition state, that is another transition state, that is leading to this green product, that is the more substituted alkene, the Saytzeff product, that is lesser in energy compared to the first one. So the stability of the double bond that is already failed in the transition state. So that is why our final product, that is according to the Saytzeff product, that is more substituted alkene, that will be the major. Both of them will be followed. Sorry, both of them will be produced, but one of them will be major, and that one is the more substituted alkene. You can see the final product stability, that is also more stable is this one. Okay. So in the transition state, increased stability of the most substituted double bond is already felt, causing low energy barrier for this beta A hydrogen, that is these two hydrogens. So here also, when the leaving groups are very good, for example halide, sulfonate, this type of leaving groups, then it is just same as you have seen in case of E1. But in some cases, we can see the opposite product, that is Hofmann may be the predominant product. So when Saytzeff rule is not applicable, that we have to see. In some cases, it is not applicable. When our leaving group is very poor, suppose fluoride is the leaving group, that is also halide, but it is not Cl, Br or I, suppose fluoride. And another may be quaternary ammonium salt, N plus 8 R3, 3 alkyl group. So if this type of leaving groups are there, what will happen? The negative charge, it will develop on the carbon, that is losing the proton. So there will be some carbonyl character felt in the transition state. So here we have taken an example where the leaving group is fluoride. Now this is also beta carbon. At that left hand side you have 3 beta hydrogen. This is also beta carbon. You have 2 beta hydrogen. So the transition state, the first transition state is the left hand side beta carbon. Suppose if it is removing, then the del minus negative charge, as it is transition state, so there is partial negative charge on this carbon and there is partial negative charge on this carbon if this hydrogen is removed. That is, if this CH bond, it is when it will start breaking, at that time there will be some partial negative charge. Now this partial negative charge, that means there is some carbonyl character, C minus. So if there is some electron withdrawing group like fluorine, it will stabilize the carbanion obviously. And another reason is, we know that alkyl groups are electron donating. So with this carbanionic, that is the carbon where this carbanionic character is generating, beside it if there is some alkyl group. See, we have this alkyl group here. But if you see this carbanion, though it is not fully developed carbanion, there are less number of alkyl groups compared to the second transition state. So lesser number of alkyl group means lesser electron donating effect. So obviously when it is carbanion, we will always we will want that there should be less alkyl substituents, so that the negative charge is more stable. So that is the reason the first transition state is more stable and it will lead to this product as major. So see, now it is less substituted alkene, but still it is the major, and it is the more substituted alkene, but it is minor. So now Saytzeff rule is not followed. Now Hofmann rule is followed. Okay. So this is the first condition where poor leaving group is present, then Saytzeff rule, that is not followed, not applicable. We will see some more examples how the poor leaving group, it is leading to Hofmann products. So here we have the leaving group L in general. Now this L may be any of this halide, right? So here we are getting, this is more substituted, this is less substituted. So this is our Saytzeff product, this is our Hofmann product. H for Hofmann, S for Saytzeff. And when it is Saytzeff, as it is not terminal alkene, so obviously there will be mixture of Cs and trans, but that is not our concern. We will focus only on the ratio between this Saytzeff and Hofmann product. So when our leaving group is iodide, that is the 2 alkene, that is the Saytzeff alkene. This is Saytzeff alkene, this is Hofmann alkene. So when the iodide, that is very good leaving group, obviously this is the major and this is the minor. So here Saytzeff is preferred. When leaving group is bromine, chlorine, then also see, though it is gradually decreasing, that is from 81, now it is 72, then 67, but still you have to see that it is the major, that is Saytzeff is winning over Hofmann. But now when you have reached fluorine, now it is 30 and 70. So now it is Hofmann preferred. Okay, so as we are gradually moving from iodide to bromide to chloride to fluoride, gradually our Hofmann product is increasing. Next example. So next example also you will see the leaving group is very poor. Very poor. N plus Me3, quaternary ammonium salt. So here also you will see the Hofmann product that is measured, and we are getting Saytzeff only 2%. Now the third example, if you see, now the leaving group is not poor, it is very good leaving group. So that is the reason now we are getting Saytzeff as measured and Hofmann as minor, that is a terminal alkene. So I hope how the poor leaving group, it is leading to the Hofmann products, it is clear from all these examples. So this is the first condition where you will get Hofmann products in case of E2, that is the condition is your leaving group is very poor. The second condition is when the proton to be removed is in the sterically more hindered position or the base is bulky. So the two examples that are given in the box, here we will see that when the base is bulky, what happens. In both the examples, our starting material, alkyl halide, that is same. Both the cases, that is 2-bromobutane. But what is the difference? In the first case, we are using ethoxide base, ETO minus. In the second case, we are using potassium tertiary butoxide, which is very bulky if you compared with this base. So in the second case, our base is bulky. So obviously, if you look at these two beta hydrogens, this is also beta hydrogen, this is also beta hydrogen. So approach of this bulky base towards this beta hydrogen, it is very difficult. Compared to that, the approach of the bulky base towards the hydrogen, towards the beta hydrogen, which is on the left hand side, that is preferred. So if that is the case, then obviously Hofmann product will be measured. But in the first case, as the base is not bulky, so simply we are getting Saytzeff product as the measure. In the next example, we will see that how sterically more hindered substrate, it will lead to the Hofmann as major product. So here our starting material is 2-bromo-2-methyl butane, which is very bulky. Now if you look at the two beta hydrogens, this is one beta hydrogen, these two are another beta hydrogen. Our base is also bulky. Actually in this example, both the conditions are present. That is your starting material substrate, that is also bulky. Base is also bulky. So obviously these two will reinforce each other and Hofmann will be the major. So the bulky base, obviously its approach, it is difficult towards this hydrogen, but the approach will be easier towards this hydrogen. Fine. So not only for bulky base, the substrate is also bulky, that is another reason. So finally we are getting this more substituted alkene, which is Saytzeff as 28%, but the Hofmann product, that is the terminal alkene, that is the less substituted alkene, we are getting as measured, that is 72%. Okay. So this is the second condition. Actually in this point, there are two conditions you can see, right? So poor leaving group, starting material is sterically very hindered. I mean the beta hydrogens that are very hindered positions. And the third point is the base is bulky. So if these conditions are present, then you can say that in E2 elimination, Hofmann will be predominating. Now we will see some cases where irrespective of the mechanism, whether it is E1 or E2, the following observations you will always see. So some other factors are playing role. So we will have to focus on those factors more, irrespective of the mechanism. So the first condition is when the formation of double bond can lead to extended conjugation, which is already present with already present functional groups. Suppose in the starting material you already have some CC double bond, or you have some CO double bond, or you have some aryl ring. So what will happen if that is already present and now you are generating one more double bond? So if these two double bonds, or suppose the newly generated double bond is close to carbonyl group or aryl ring, there will be some probability of conjugation. So that conjugation will lead to the major product. That is, see this example, here we already have a CC double bond, right? This is our alpha carbon. Now this carbon is one beta carbon, this is another beta carbon. Now if you remove hydrogen from this side, then you will get this molecule. Suppose this is A, this is B. So B product, how you are getting? By removing the beta hydrogen from the right hand side. But if you remove the beta hydrogen from the left hand side, you will get A. Now why A is major product? Because of the conjugation that is present in this molecule. This type of conjugation, it is not present in the product B. So that is why this B will be predominating over, A will be predominating over B because of the conjugation. So this is the first case. Okay, another example regarding this. Now in the starting material, see, we have a phenyl group already present. As we have said that CC double bond or aryl group, any of these three if it is present, then we also have to consider the factor which is conjugation. So phenyl ring, when it is present, this is our alpha carbon, this is one beta carbon, this is another beta carbon. So if you are removing this beta hydrogen, that is the right hand side beta hydrogen, what product you will get? You will get this product. But if you are removing the right hand side beta hydrogen, any of these two hydrogen, you will get this product. So obviously, as in the first product, the double bond is in conjugation with the aryl ring, so obviously it will be the major product. Okay, but here there is no such conjugation possible, so that is why it is minor product. Fine. So in the first example, in the starting material, we already have a CC double bond. In the second example, in the starting material, we already have a aryl ring. So that is why the question of conjugation is arising. Another case is elimination in the bridged cyclic compounds. It will follow the Bredt's rule. Now what is Bredt's rule? An empirical observation that a double bond cannot be at bridgehead carbon unless the ring that contains the double bond contains at least 8 atoms. So suppose it is less than 8 atoms. Then if you are forming a double bond in the bridgehead carbon, and double bond carbon means sp2 carbon, so if it cannot attain planarity, obviously double bond will not be formed at the bridgehead position. So that is the reason. Now another thing I want to mention, that when it is large number of atoms are present, that is if the ring contains more than 8 atoms, so obviously there will be some more flexibility. In that case, the sp2 carbon of the alkene CC double bond, it can attain planarity. But if it is less than 8 atoms, for example, if you consider this molecule, this is 6 membered, right? This is 6 membered. So obviously, if the double bond is formed at this position, then planarity is not possible. But if the double bond is formed here, then planarity is possible. So that is why this molecule is formed. So again, see what it is written here. Elimination in bridgehead cyclic compounds follow the Bredt's rule. A double bond never goes to bridgehead carbon in the rings of smaller size, that is less than 8. As having a double bond on the bridgehead, it will be very unstable as it cannot attain planarity. So if you consider this carbon as alpha, this is beta carbon, this is also beta carbon. So here we have hydrogen. So this hydrogen can be removed. Any of these two beta hydrogen, that also can be removed. But if you are removing the hydrogen from this carbon, then you will get the second alkene, which is not very stable, very unstable. So that is the reason here the major product is this one. So these are some conditions where irrespective of E2 or E1, some other factors are playing role. So that is the reason we have to take care of those extra factors also. So that is all about the regiochemistry of E1 and E2. I hope you have some clarity now regarding this regiochemistry in E1 and E2 mechanism. That is nothing but when Saytzeff product will be predominating or Hofmann product will be predominating, and we have also seen that irrespective of E1 and E2 mechanism, what are some other factors in the starting material, that is depending on the design of your starting material, how the products are changing, how we are getting different types of regioselectivity. All these things we have discussed here. So if you find the video helpful, please like, share and subscribe. I will come to you with the next video of elimination, which will be regarding E1CB mechanism. Until then, goodbye.